Right, continuing our work in Unit 2, we're now on Lesson 4, and Lesson 4 is going to be involving derivatives of combinations of power functions. The combinations we're going to be looking at could be sums of power functions, differences, a constant multiple times the power function. The constant function rule, I think we've already gone over that one. We've already proven that one, so I don't feel the need to prove that one again. And again, I'm going to remind you what the power rule was. If the function is x to the n, then its derivative is n times x to the n minus 1. This is Lagrange notation. If I want to use Leibniz notation, I will put d by dx. And in brackets here, instead of y, instead of dy over dx, I'm going to put the function that I'm taking the derivative of right here. I'm going to skip this slide because we did already prove this, but again, why does this make sense? If you are a constant function, then you are a horizontal line. The slope of a horizontal line is 0, so it doesn't matter where I position this horizontal line, its derivative is always going to look like that. It's going to sit right along the x-axis because the slope will always be 0. All right, so the purpose of this slide would be if I was presenting to you in class, I'd have you match up the proofs. I don't really like you to do the teacher says that the difference rule is this without proving it. So these are the proofs. One is the constant multiple, one's the constant function, one's the difference, and one's the sum. You're going to match the proof to the correct rule. Again, if you want more time to think, you can be in charge of the timing. I'm sort of just going to move forward here. This one we already did. I don't feel the need to go over that one. And this particular one, since this is a general proof, maybe we'll go over this one a bit. So f is equal to k times g. So f at x equals k times g at x. So f at x plus h, and that's a k, so, and not an h. So f at x plus h would be k times g at x plus h. And minus k times g at x would be f at x. The k can come out in front. Now the k here is independent on the variable for the limit. So in fact, it can come outside the limit. We had already seen that earlier. So it can come outside the limit. Factoring the k out and then bringing it out in front is just going to leave me with g at x plus h minus g at x all over h. And by definition, of course, that's g prime. So if f at x is equal to k times g at x, then f prime at x is k times g prime. That's the constant multiple. This one is the sum and the difference. This one is our sum because we're adding here. We're adding here. This one is the difference because we're subtracting. So f is going to be p at x plus q at x. So f at x plus h would be p at x plus h plus q at x plus h minus f at x, which would be p at x plus q at x. If we distribute, we can match them this way. We can match p at x plus h minus p at x together, and I can group q at x plus h minus q when I distribute together. Now, we talked about the limit of a sum being equal to the sum of the limits. So I can break these apart this way. First of all, if I'm going to break them up this way, I can break up this quotient this way to be p at x plus h minus p at x all over h, plus q at x plus h minus q at x all over h. That's equivalent to this. And now the limit of the sum is going to become the sum of the two limits. And of course, this limit here, that's just the definition of p prime. And this one over here is the definition of q prime at x. And then you can take some time to walk through the difference one. It's done the exact same way, only we have a minus here. And when we do that particular one, when we distribute, we're going to get negative here, and we're going to get a positive there. So when we go to split them apart, I'm going to factor a negative out of these two terms here. So I'm going to have p at x plus h minus p at x all over h minus q at x plus h minus q at x because I factored a negative out. And now this is the difference. The limit of a difference becomes the difference of two limits. I now have P prime here, and I have Q prime there. So those are the proofs of those. And now we'll apply them. So in this particular case now, are these all power functions? Yes, they are. And these are sums and differences of power functions. So I can use these rules here to split them apart. I'm going to walk you through this first one, and I'm going to show you how I would do this. So the properties of derivatives tell me, the sum and difference rule tell me to take the derivative of the first term plus the derivative of the second term plus the derivative of the last term. And the derivative of negative 3x squared would be negative 3 times 2, which is negative 6. 2 minus 1 is 1, so it's negative 6x. The derivative of 10x, if you'd like, that's going to be 10 times 1 times x to the 0, which is just 10. But we also did prove that the derivative of a times x would just be a. So we know the derivative of that is 10, and the derivative of 4 is 0. So f prime at x is negative 6 plus 10, negative 6x plus 10. So I'm going to use this to show someone what my thinking is, and I'm going to advise you that you should take a similar philosophy, because when people mark something, they're expecting to see it look a certain way, and if you write it a different way, they might have difficulty following. So when you put d by dx, that is an operator. What operation am I going to apply to this? I am going to take the derivative of this. So now it's clear what I'm doing in my work. So I'm going to suggest you make use of d by dx to show the operation you're going to apply to the terms. All right, moving on to the next one. We do have a difference of two terms. Are they both power functions? That's the first question I'm going to ask you. This one is definitely a power function. This one is not. The quarter is inside. So again, I'm going to have to make use of this rule. A times x all to the n, or x, in this case, x over a all to the n. That's x to the n over a to the n. So we're going to have to massage first. So step one, massage first. Massaging first, we get 1/4 to the negative 1/2 times x to the negative 1/2. As I mentioned, that's already a power function. 1/4 to the negative 1/2 is going to become 4 to the 1/2, right? So flip the base, and the exponent becomes positive. The square root of 4 is 2. So f at x is now 2x to the negative 1/2 minus 2x to the 4/5. These are both power functions now, so we can now take the derivative. And just again, a reminder that if your function is a times x to the n, then its derivative is a times n times x to the n minus 1. All right, so moving on to the next slide to go through this. Again, I'm going to just show you this step using d by dx as an operator. This is how you tell someone you intend to take the derivative of this term, and I intend to take the derivative of that term. Then showing my work. To take the derivative of this, it would be 2 times negative 1/2 times x to the negative 1/2 minus 1 minus 2 times 4/5 times x to the 4/5 minus 1. 2 times negative 1/2 is negative 1. Negative 1/2 minus 2 over 2 is negative 3 over 2. So negative x to the negative 3 over 2. 4/5 minus 5/5. 4 minus 5 is negative 1. So I get negative 1/5. So the derivative is negative x to the negative 3/2 minus 8/5 x to the negative 1/5. All right, we'll move on to the next one. Again, find the derivative using the most appropriate notation, Leibniz when it's y, prime notation when we're using f, g, or h or something at x. Step one, we're going to look at this. Are these all written in the proper form? Are they all power functions? If they're not power functions, then we're going to have to massage first and write them as power functions. Again, you can be in control of the timing and stop anytime you wish if you want to give it more thought. They're not all power functions. The first one and the third one were. The middle one I'm going to have to rewrite as 2 times x to the 1/3. Now they're all written in power function notation. I'm now ready to take the derivative. Remember, I had suggested that I'm going to start by writing d by dx, write that as an operator, so I can show people what I am intending to do. Why is that a good idea? Because if someone can't follow your work when they're marking it, high school we tend to be very generous and spend many hours trying to figure out what it is you're doing. University, not so generous, so you might want to take advantage of using that symbol to make it clearer what you're doing. So d by dx of the first term plus d by dx of that second term. I got to fix this. I'm seeing an error there. Are you seeing an error there? Like that. Whoops. Back that up. Back that up. There we go. So it is 2x to the 1/3. It's supposed to be written that way. There we go. If I write it this way, it has a different meaning. 2x to the 1/3 would not be written as a power function. I changed the meaning by writing it that way. That's not the way it is written. It's 2 times x to the 1/3. So I had the bracket in the wrong spot. Derivative of that term plus the derivative of the last term. And again, these are power functions. So 4 times 3 is 12. 4 minus 1 is 3. I tend to just go to the derivative when they're nice and friendly, but when there are fractions, sometimes I will write that exponent down just to give myself some time to think. 2 times 1/3 is 2/3. The new exponent becomes 1/3 minus 1. 1 over 3 minus 3 over 3. 1 minus 3 is -2, so that exponent becomes -2/3. Again, because the exponent's a fraction, maybe I'll show a bit more work. -3/4 x to the -3/4 minus 1. -3/4 minus 4 over 4. -3 minus 4 is -7. So the derivative of this is 12x cubed plus 2/3 x to the -2/3 minus 3/4 x to the -7 over 4. Now, why is it advantageous to put this step in? Because this is correct. It shows what I'm doing. If I then make a mistake simplifying coming down to here, I will still get partial credit for having this right. If I jump from here straight to there, but I've made an error with my fractions, and again, when you have fractions, you're more likely to make errors, then you will not get credit for that. So I would advise putting that line in when you're dealing with fractions. All right, so that's it for 2a. Let's try 2b. Is this in the proper form? Is it ax to the n? And you might argue, well, all of these little pieces are ax to the n, but this is a product. This is a product of some power functions. We have no idea at this point how to take the derivative of a product. So what we're going to do is expand. And the next lesson I will teach you how to take derivatives of products. But in this case, we can expand. We don't know how to do it, so we're going to expand. 2x squared minus 6x plus 5x is minus x. 5 times -3 is -15. This is the exact same function as that, but this one is written in a form in which I can take the derivative. So I'm just going to move forward now and take the derivative of this one. I didn't bother to write d by dx in front of these guys because these all look like they were simpler. The derivative of 2x squared is 4x. The derivative of -x is -1. Of course, the derivative of a constant is 0. So h prime here is just 4x minus 1. Let's move on to the next slide. Find the derivative of this using the most appropriate notation, either Leibniz or prime. Just want to make sure I did use the proper notation there, because sometimes I forget when there's a y to use y prime or dy by dx. All right, let's come over here. What are the issues with this one? First thing I hope you're noting is this is a quotient, and she did not tell us anything about how to take the derivative of a quotient. That will be 2 lessons from now. So there must be another way to do this. You see how this is a single power function? When it is a single power function, my advice to you is massage first. This divided by this, this divided by this, this divided by this. And my advice will always be, when the denominator is a single power function, even when I teach you the quotient rule, is not to use the quotient rule when you don't have to. It's going to overcomplicate things, and in the end, you're expected to simplify down to the most simple answer. So you're overcomplicating things if you attempt to do that. So again, single function, single power function in the denominator, you will always do divisions on each term. Use the exponent laws for dividing 2 powers with the same base. X to the n divided by x to the m is x to the n minus m. So that's what I'm going to do next. I'm going to massage first. And in this case, we're forced to massage because we don't know the quotient rule. But if we did do the quotient rule, if we did know it, I'm advising you don't apply the quotient rule in this case because it's a single power function. We'll see later if I'm dividing by something like this, I have no choice but to use the quotient rule because I have 2 terms here. All right, so what's going to happen now? This is going to be x to the power 1 minus 4, using the exponent law, number 2, dividing two powers with the same base, plus 3x. This one is x to the 1/2, so 1/2 minus 4, minus 4. This is x to the negative 4 minus 4. So I get x to the negative 3, 1 minus 4 is 3, 1/4 minus 8/4. Remember, it's not 1/4, sorry, 1/2 minus 8/2. So a half minus 4 is 1/2 minus 8/2. 1 minus 8 is negative 7. So that exponent is negative 7/2. Negative 4 minus 4 is negative 8. So now this function is equivalent to this function in terms of derivatives. So now what we're going to do is take the derivative of this. And I personally would rather take the derivative of a sum or difference of power functions than the derivative of that piece. So the next step now is for you to take the derivative of that. Again, I'm going to move forward, but if you want to go slower, you can control the timing yourself. Notice this particular time I decided not to put d by dx in front of each of these because I felt these were simpler ones to do. If you want to put d by dx in front of each of them, you can. Negative 3, so there's y. If I want to take the derivative, negative 3 comes out in front. X to the negative 3 minus 1 is negative 4. To take the derivative of the next piece, I'm going to get 3 times negative 7/2. 3 times negative 7/2 is negative 21/2. Now negative 7/2 minus 1. I'm going to show that because sometimes when the exponent is a fraction, kids have difficulty performing that operation. So I'm going to leave it like that so I can show someone I did it correctly. This is negative 4 times negative 8 is positive 32. This is x to the negative 8 minus 1, which is negative 9. You decide if you need to put that in as an exponent. If you accidentally wrote negative 7, you wouldn't get credit for that. If you wrote negative 8 minus 1 and then wrote negative 7 on the next line, you would get partial credit because at least this part is right. Now, negative 7 over 2 minus 2 over 2 is negative 7 minus 2 is negative 9. So in the end, the derivative is negative 3x to the negative 4 minus 21 over 2x to the negative 9/2 plus 32x to the negative 9. And again, star this one. I always put this one on tests or performance tasks. And again, I want you to massage first. That's the simplest way to do it. All right, find the equation of the tangent to this curve. Again, very popular question. I think this might be the third time we've done a find the equation of a tangent to a curve. So in order to find the equation of the tangent, you need the slope of the tangent. So the first thing we're going to have to be finding is what is f prime at 1. That's the slope of the tangent at the point 1, 2. Before I can do that, I need f prime at x. And what do we know how to do? We know how to take the derivatives of power functions. Sums and difference of power functions. So this is written as a power function. This is not. This is not. They can be written as power functions. And the next thing we also have to worry about is there is a sum here, but I've got a product out in front. So I'm going to have to write as power functions and then expand. So that's your first step. You got to massage first to make this a sum and difference of power functions. Again, you can be in control of the timing. I'm just going to move forward. So this is x to the negative 1 times x squared plus x to the negative 1. This is multiplying two powers with the same base, so I should add the exponents. This is x to the negative 1 plus 2 plus x to the negative 1 minus 1. This becomes x, and that becomes x to the negative 2. So there's my function. I've now written it as a sum of power functions. Step number 2 would be for you to find the derivative of this function. And that's what I'm going to show you on the next slide. So the derivative of x is 1, and the derivative of x to the negative 2 is negative 2 x to the negative 3, negative 2 minus 1. After we've done that, we now have the slope of the tangent anywhere. Initially I said we need y prime at 1. So now you're going to find what y prime at 1 is by plugging 1 into there. So let's look at that on the next slide. All right, so the derivative is 1 minus 2x to the negative 3. I want to find the tangent, slope of the tangent at 1, 2. I will now plug a 1 into here. 1 minus 2 times 1 to any exponent is 1, and 1 minus 2 is negative 1. So I now have the slope of the tangent. And then as a reminder, we are always going to be plugging into this point slope form equation, y minus y naught times x minus x naught. It's the fastest way to do it. And I will show you that on the next slide. Again, you're in control of the timing. Pause whenever you feel you need to. So y minus y naught, the y coordinate is 2, is equal to m, the slope is -1, times x minus x naught is 1. So y minus 2 equals -1 times x minus 1. And we can just leave it like that. Now, -1, we didn't have to write the -1, so on the next line I just wrote it as y minus 2 equals -x minus 1. And as I mentioned, you can leave it in this form. It's acceptable for university. It is acceptable here. But if you are a slope y-intercept person, you would then have to expand and say this is y minus 2 is equal to -x plus 1. And if you bring the minus 2 over, you will get plus 3. So slope y-intercept form is this equation here. But again, it's not mandatory for you to do that. You can simply leave it like that. All right, next question. A subway travels from one station to the next in 2 minutes. Its distance in kilometers from the first station is given by this formula. At what times will the train have a velocity of 0.5? Now, this is position function, velocity. So how is velocity related to position? Pause if you don't want the answer, if you want to think about it. V at t is equal to s prime at t. So I need to take the derivative of the position function. Now, what is this question asking me? When is the velocity this? So what I need to solve is when is 0.5 equal to v at t? Because that's what they're asking me. So I'm going to translate this from English to calculese, if you like, if calculese is a language. I want to know when 0.5 is equal to v at t. Of course, that's also s prime at t. So first step, take the derivative of the position function. This function is already written as power functions, right? This is a difference of power functions. Should be straightforward for you to take that derivative. I'm now going to move forward to show you that on the next slide. So s prime at t or v at t, the derivative of t squared is 2t. The derivative of 1/3 t cubed is 1/3 times 3t squared, and 1/3 times 3 is 1. So the velocity would be given by this function, 2t minus t squared. Then you need to find when the velocity is 0.5, so you want to plug in 0.5 there, and you want to solve. I'll give you a bit of a hint though. So we are 2t minus t squared. I might multiply this whole thing by 2 so I can clear the fractions because I'd rather not work with fractions. Moving forward to show you that on the next slide. If I bring this over, t squared minus 2t plus 0.5 is 0. That gives me 2t squared minus 4t plus 1 is 0. And then you can attempt to see if that's factorable. I'm not sure if I discussed it on other videos, but if b squared minus 4ac is a perfect square, you're factorable. How do I know that? Because I need a rational number back in the quadratic formula. This is the only bit that might be irrational. We've got the square root of something. And if this number under here is not a perfect square, then you're going to get something like this. Not factorable because it's irrational. But if you get a perfect square, that will return as 2, and now you would be factorable. If the roots are rational numbers, you're factorable. If the roots are irrational numbers, you're not factorable. So check the discriminant, see if it's factorable. So moving on to the next slide. The discriminant is b squared, that's -4 all squared, minus 4 times a times c. That gives me 16 minus 8, which is 8. 8 is not a perfect square. It's not factorable, so we're just going straight to the quadratic formula. I'm going to do that on the next slide. Again, you're in charge of the timing. You can pause if you wish. All right, quadratic formula is -b. So a -b is +4 plus or minus the square root of. No need to write b squared minus 4ac because we've now figured out that's 8. So I'm going to plug in the 8, all divided by 2 times a. 2 times a is 4. Now we have to rewrite root 8. I'm just going to remind you that that's the square root of 4 times 2. We do have to reduce these. The square root of 4 is 2, so this is 2 root 2. So that is as a the radicand is now in lowest terms, or it's a radical number in lowest terms. So 4 plus or minus 2 root 2 all divided by 4. 4 divided by 4 is 1, so 1 plus or minus 2 over 4 reduces to a half, so that just becomes root 2 over 2. So t equals 1 plus or minus root 2 over 2. Now I am now going to convert these to decimals to see if both of these are admissible. It did tell us in the next 2 minutes. So that tells me that the domain is between 0 and 2 inclusive. So 1 plus root 2 over 2 is 1.71 minutes. 1 minus root 2 over 2 is 0.29 minutes. They're both in the domain 0 to 2, so both roots are admissible. All right, so that would bring us to the end of the typical problems we would do in class. Straightforward ones. Now, more challenging thinking ones. We would not be able to do all of these in class, so I'm going to walk you through the solutions to all 3 of these, but remember, in a typical class, we would not be doing all 3 of these. We would be lucky to be able to get to 1 of these. So let's start with the first one. The tangent to the cubic function, defined by this, at 0.40, it intersects the curve at another point B. Find the coordinates of B. How are we going to do this? Again, if you want more time to think, you could sort of pause and take as long as you need. If I want to find where it's going to intersect, I'm going to need, I've got the equation of my tangent, so let's just call that mx plus b, if we like. I'm going to need the m, I'm going to need the b, and then I'm going to say, where is that equal to x cubed minus 6x squared plus 8x? And that's how I will find the second point of intersection. It'll give me both points of intersections, but I want the second point of intersection. So what you're going to need to do is find this. That's your starting point. Find the equation of the tangent. How will you do that? You're going to take the derivative of this first. That's f prime. You're going to plug a 4 in. That's f prime at 4. That's the slope of the tangent. You can plug into this to find the equation of the tangent. We are now going to have to write this, though. We are going to have to isolate for y here so that I can set up this equation. So that, in a nutshell, is how this particular question would be done. I'm now going to move forward to walk you through the whole entire solution. So as I said, the first thing I'm going to do is take the derivative. The derivative of x cubed is 3x squared. The derivative of minus 6x squared is minus 12x. The derivative of 8x is 8. I now need y prime at 4, so I'm going to plug in a 4 here. 3 times 4 squared minus 12 times 4 plus 8. Punching all that into your calculator, 48 minus 48 plus 8 is 8. So y prime at 4 is 8. I now need the equation of the tangent. So I'm going to plug into y minus y naught. Y minus y naught is 0 times m. The slope of the tangent is 8, so I plug in an 8. In brackets, x minus x naught is 4. So y minus 0 is y, so y equals 8x minus 32. That is the equation of the tangent. And as I mentioned before, now we want to find where that equation of the tangent intersects this curve, because it intersects it at some other point. So I'm now going to write 8x minus 32 is equal to x cubed minus 6x squared plus 8. This is how you find the points of intersection. If we isolate now, we'll get x cubed minus 6x squared. 8x minus 8x is gone, bringing the negative 32 over, I get plus 32. So I now need to find the roots of this. I am not going to use the entire factor theorem as presented in advanced functions because I do know that it intersects already at the point of tangency, which is 4. So I do know that x minus 4 is a factor, so I'm just going to go straight to using 4 because I know 4 will work. Again, I'm going to repeat that. How do I know 4 will work? Because the tangent intersects the curve at the point of tangency. It's passing through the curve. It's touching it there. So now setting up for a synthetic division. 1x cubed minus 6x squared plus 0x plus 32. The 1 comes down. 1 times 4 is 4. Negative 6 plus 4 is negative 2. 4 times negative 2 is negative 8. 0 plus negative 8 is negative 8. 4 times negative 8 is negative 32. 32 plus negative 32 is 0. I can put a little happy face there. There we go. I expected the remainder to be 0. And so now I'm left with x squared minus 2x minus 8, which I will now factor. X squared minus 2x minus 8, two numbers that multiply to negative 8, and they add to give negative 2. Those numbers would be negative 4 and positive 2. So this factors into x minus 4 times x plus 2. We'll just verify. There's x squared plus 2x minus 4x. There's minus 2x, negative 4 times 2, negative 8. So it does work. So now we can see there's a point of intersection at 4. Well, we already knew that from there. And then here's the other point of intersection. It intersects when x is negative 2. I now need the y coordinate, so I'm going to plug negative 2 into here. Negative 2 all cubed minus 6 times negative 2 all squared plus 8 times negative 2. That gives me negative 48. I now have the second point of intersection at negative 2, comma negative 48. I'm going to back you up to the second one now. Let P at AB be a point on the curve. The square root of x plus the square root of 1 is 1. Show that the slope of the tangent at P is negative b over root a. So the first thing we're going to have to do is we're going to have to find the slope of the tangent. So you're going to have to isolate this. 1 minus root x. You're going to have to isolate this for y, so you're then going to have to square this whole thing. I cannot take the derivative of this until it's isolated for y. So isolate for y, take the derivative. And then once I take the derivative, I'm going to have the slope of the tangent, and it wants me to show that the slope of the tangent at the point A, B is negative b over a. So you would then have your slope of your tangent here. You're then going to plug in your a and b, but I am going to caution you to remember that the square root of a plus the square root of b, or actually not a caution, it's a hint. The square root of a plus the square root of b is 1 based on this, if AB is on the curve. All right, so now I'm going to walk you through that. We had a discussion. If you want more time to think about this or try this on your own, you can pause the video at this point. I'm just going to move forward. As I mentioned, step 1 now, I can't take the derivative written this way unless I knew implicit differentiation, which we don't know at this point. So root y is negative root x plus 1, squaring both sides, y squared, or root y all squared is y, negative root x plus 1. I can't take the derivative of this because I don't know how to. I just know how to do the sums and differences. So I'm going to expand this. Negative root x all squared is positive x. Negative root x times 1 times 2 is negative 2 root x. 1 all squared is 1. There we are. So isolate this for y. I get this particular function. I can now take the derivative of this. So y prime, the derivative of x is 1, minus 2 root x. So minus 2, remember root x is x to the 1/2. So I would be 1/2, which I chose to write as 0.5, times x to the, so the derivative would be 1/2 times x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. So it would be negative 2 times 1/2 times x to the negative 1/2. But negative 2 times 0.5 is 1, so I'm negative 1. I'm now going to put this in the denominator. X to the negative 1/2 is 1 over root x. So the derivative is 1 minus 1 over root x. And then what I'm going to do is a common denominator. I'm going to multiply this by root x, and then root x minus 1 over root x. So the derivative in the end is root x minus 1 over root x. And we can verify root x divided by root x is 1 minus 1 over root x. So those two are indeed equal to each other. Now I need to find the derivative at a, y prime at a. So I'm going to plug in y prime at a, and I'm going to get root a minus 1 over root a. And now that little hint. So we can see the root a, right? Now how am I going to show this is negative root b? So they did say the point AB is on the curve, so root x plus root y is 1 is going to give me root a plus root b is 1. And if I isolate this for root a minus 1, bring the 1 here, bring the root b there, I get root a minus 1 equals negative root b. That means I can replace this with negative root b. So I now have negative root b over root a. The negative can come out in front, and I can write that as root b over a. Just a reminder that root x over root y is equal to root x over y. I'm presuming, of course, that y and x are greater than or equal to 0. All right, one last thinking problem to look at. For this function here, f at x equals x to the n. Find the x-intercept of the tangent to the graph at this point. So find the equation of the tangent, then find the expression for the x-intercept. Then what happens to the x-intercept as n increases without bounds? So step one, you're going to need to find f prime at x. Then we're going to need to find f prime at 1. And after we found f prime at 1, we want the equation of the tangent at 1, 1. Then after you do that, we want the x-intercept of that equation. And after we found the x-intercept of that equation, then the last thing we're going to do is we're going to do the limit as n goes to infinity of the x-intercept, and we're going to see what's going to happen. So those are the 5 steps you're going to need to solve this particular problem. Again, you're in control of the timing, so if you want to pause and try this on your own, you can. I'm just going to walk you through all of those steps right now. All right, step 1, find the derivative. F prime at x is n times x to the n minus 1. That's not too bad. F prime at 1, I'm going to plug in a 1. N times 1 to the n minus 1. Well, 1 to any exponent is 1, and n times 1 is 1. So there we are. We've now found the slope of the tangent. The slope of the tangent at 1 is n. The equation of the tangent line would be y minus y naught. Y naught is 1. The slope of the tangent is n times x minus x naught. X naught is 1. So now we have the equation of our tangent. And then the next thing we said is we need the x-intercept. So we're on to step 4 now. So that was step 1, step 2, step 3. We're now on to step 4. To find the x-intercept, I need to let y be 0. So I'm going to plug a 0 in here. I get 0 minus 1 is n times x minus 1. So negative 1, I will divide by n to isolate for x minus 1. Negative 1 over n equals x minus 1. So x is equal to 1. When I bring that over, that will become positive. 1 minus 1 over n. So there is the x-intercept. And now the last step is to look at the limit. That's step 5. The limit as n goes to infinity of 1 minus 1 over n. So let's think this through. As n goes to infinity, 1 over n, because we already talked about this before, 1 over infinity approaches 0 positively. And this would be 1 minus 0, and that would be 1. So as this n approaches infinity, the x-intercept of the tangent through the point 1, 1 is going to start approaching 1. All right, that brings us to the end of this particular lesson. We were looking at derivatives, combinations of power functions. That's what we did, applying mostly the sum and the difference rule, and of course making sure that we were a power function before we did anything. We looked at several examples, and then we finished off with some interesting challenge problems coming from trying to help you become better thinkers. So that brings us to the end of this lesson. The next lesson we would look at would be focusing on products, and then after that we would look at quotients. So that brings us to the end of this lesson. Hopefully you have learned something new. If you've made it to the end, once again, thank you for watching, and as always,